All right, we have very little time. I was hoping for a couple hours. They've given me precisely 45 minutes. So we're going to move as quickly as we can through all the normal stuff. First and foremost, every single presentation I do, I start off that presentation with this slide. On this slide, you're going to find the code. Code's important. You can follow along later on at your own leisure, your own discretion, to see what we've done. You've got my coordinates. So should you want to reach out, if you have questions, comments, feedback, whatever, don't hesitate to reach out to me on the Twitters. How many of you are on Twitter? I'm always curious about this kind of thing. Twitter. OK, the rest of you, get on it. You're doing it wrong. It's a great place to be. It's the new IRC. It's where all the developers that drive the open source that power your business are. So you owe it to yourself to be there. What about email? Email. Who's using email? Who's using email? OK. Awkward. Moving on. A little bit about me. My name is Josh Long. I'm a Spring developer advocate on the Spring team. I do training videos in Safari. I've got a book called Cloud Native Java. I've got a podcast every Friday called The Beautiful Podcast. I do a weekly roundup every Tuesday called This Week in Spring. I do a weekly series every Wednesday on YouTube called Spring Tips. It's just me at a keyboard. I've got a new book called Reactive Spring coming out. All these are things on which I'm working or going to be working on. And they're things that I care about. And these days, a lot of the time, the thing I most find myself interested by is reactive programming. And reactive programming is precisely what we're going to talk about today in our brief time together, our less than 45 minutes together. Reactive programming is a new response to a very old question. How do I scale up my applications? And for some definition of scale, right? I want to take my existing application and be able to handle more requests, more users, more demand. How do I do that? And in order to appreciate the problem, we need to consider why we have the problem, right? In order to appreciate that, we need to think about what got us here in the first place. For most of us, up until, let's say, 12 or so odd years ago, it was fairly easy to scale up our application, right? We didn't have a whole lot of users, and we didn't have a whole lot of demand, so we had fairly well-known, fairly well-understood scale patterns. But then we have the arrival of cloud computing. We have the arrival of the API-driven economy, driven by things like IoT and big data and NoSQL and microservices and all these things that result in more API calls. And suddenly, we have more need to scale. And so the question then is, why do we need to scale? Because we want to handle more requests, more users. Why do we want to handle more users? Why can't we just do so on the existing machine that we've got? What are the things that are bottlenecking us, that are making it so that we can't handle more users or more capacity on one machine? Why scale out at all, actually, if we could just handle more users on the same machine? And in order to really appreciate that, we have to appreciate some of the bottlenecks. Now, the biggest bottleneck that you can pretty easily kind of arrive at if you kind of profile a modern system today, especially a microservice-y sort of cloud-native system today, is that a lot of the work that we do in a given application is that of I/O. It's input and output. It's the movement of data from one place to another, right? And this I/O is pretty understandable, right? We're doing network calls, database calls, message queue calls, all this work over the wire. And that work is not such a big deal in of itself. That's what we are trying to do. The problem is that in order to do that work, a lot of the code that we've used in the sort of previous 20+ odd years is based on java.io. Right? And here we have synchronous and blocking input and output. That synchronous and blocking input and output requires that we sit on a thread. Right? When we say blocking, what we mean is that in order to execute that code, you need to sit on a thread waiting for those bytes to arrive. You send bytes out and you wait. You expect new responses to come back in and you wait. And so we're doing all this work. Well, actually, we're not doing any work at all. We're just waiting, but we're sitting there on threads. Look at most computers today, and you're going to find that they're dramatically underutilized, right? They've got tons of processing power, but they're just idle, right? A lot of it is just idle time, waiting for bytes to be conducted over the network. And this is a bit of a problem. The reason it's a problem is because we can't just create more threads. Threads are expensive. Right? This is one of the limitations that we see with sort of the existing approach to building applications, that if we had infinitely cheap threads, this might be less of an issue, but unfortunately, the way that we write our code at the moment is in such a shape, such a way that it doesn't lend itself to being more friendly about reusing threads, right? We have Java lang thread. Thread is a black box. We get to pretend that we have the whole computer. We can sit there and luxuriate in all this isolated process space that we have in each thread. But each thread is not its own computer. There are other things on this system that you have to share and whose resources you have to share. And we don't have any way of saying to the runtime, hey, I'm happy if you can take this thread back, if you want to reuse it for something else. If we change the way that we write code, if we think about it in terms of cooperative multi-threading, then we arrive at this idea that we need to be more explicit about how we repurpose threads, how other things can reuse those threads, so that while we're waiting for input and output, we don't sit there on the thread. We take advantage of asynchronous I/O, and while we're waiting for that input and output, we can tell the runtime, here's this thread, right? This is a good solution because it allows us to be more resource efficient with our threads. Other things can reuse the threads that we're not using. In order to do this, of course, we need to change the way that we do input and output. I mentioned asynchronous I/O, right? This is input and output where you ask for data, and then asynchronously, a few seconds or a few minutes or a few whatever later, you get a response. And in between that request and that response, you can give that thread up and somebody else can use it. This is what we want. We want to take advantage of asynchronous I/O. In order to take advantage of asynchronous I/O, and indeed to build a system based on the idea that we're going to have requests for data and then asynchronously we're going to get that data, in order to build a system that supports that worldview, we need to have a computational metaphor that maps naturally to what we're trying to do. It needs to support building software and delivering into production business value, right? After all, what good are whatever types we decide? What good are whatever ubiquitous computational metaphor that we decide to use? What good is that if it's not well integrated and ubiquitous and supported in all the different layers of the stack? Suppose for just a second here, just hypothetically, just imagine that for whatever reason, hypothetically, the technologies with which you are familiar, the APIs with which you are familiar, for whatever reason, didn't understand and didn't like Java util collection types. Imagine that just for an instance, that whenever you tried to use a Java util set in a Hibernate entity to map it 1 to n, that Hibernate didn't just throw an exception, hypothetically. It didn't just throw an exception. It actually rendered an ASCII art middle finger and then segfaulted the machine. Would you continue to use Hibernate with Java util sets if you knew that you could hypothetically expect this kind of abuse? Of course not, right? And you're not going to go out and rebuild Hibernate if what you're trying to do is to map objects to JDBC data structures. There's nothing better, right? That's the thing that it does best. You're not in the business of reinventing that wheel. Instead, what you want to do is get to production. So you're going to use whatever is the path of least resistance. This underscores my point. Today, if we want to support this new world where we take advantage of cooperative multi-threading, where we write code in terms of these asynchronous requests and responses in between which we can then free up the use of that thread, if we change our approach to writing code to support this new worldview, we need a computational metaphor that is ubiquitous. It needs to be well integrated in every layer in the stack. And this is where I think Spring offers the most compelling value. In 2017, in September, 2 years ago this month, we released Spring Framework 5.0, in which we included a brand new reactive web runtime called Spring WebFlux. And we've since then included or released a Spring Data K, Spring Security 5, Spring Boot 2.0, Spring Cloud Finchley, and so on, a number of different releases that have all now integrated reactive programming. So what we're going to do, my friends, today is we're going to take a look at all of that and see how it all fits together. All of that stuff that I just mentioned is built on top of Spring Framework 5. Spring Framework 5 is in turn built on top of Reactor. And Reactor is in turn built on top of the reactive stream specification. These are 4 different interfaces, 4 very simple interfaces that are well integrated, well deployed. They're ubiquitous. If you understand how to use them, then you can use them at every different layer of the code. Okay, so that's our modern day reactive asynchronous non-blocking equivalent to a Java collection. Okay, so save this. Good, and we're going to build a new application, as we always do, as I always like to do. We're going to build some software today, of course, by going to my second favorite place on the internet after production. Of course, I love production, right? I love production, and you should love production. You should go as early and often as possible. Bring the kids, bring the family. The weather's amazing. It's the happiest place on earth. It's better than Disneyland. But if you have not been to production, you can begin your journey here at start.spring.io. So we're going to build a new application today. Using Spring Boot 2.20 M6, we're going to build an application taking advantage of a few things here. We're going to specify that we're going to build an application called the reservation service. We're going to specify a few options here, right? The choice of packaging, right? People sometimes get confused about which option to choose and when, but I'm going to explain here now when and where to choose which. If by some freak fluke of physics, some terrible tragedy of time-space, you find you are somehow transported to the distant, distant past, then use .war. But if you're here with us in 2019, then use .jar. Okay? And then we have the choice of packaging. People get we have the choice of JVM version. Which version of the JVM do you want to use for your application today? We have 3 options, of which only 2 are acceptable, are okay, are correct. 8 is not a correct version. Okay? The current long-term supported version of Java is 11. The current version of Java is 12. And by the way, I think it's like tomorrow, right? Or the next day when 13 comes out. So very soon, 12 will no longer be correct. It'll be the wrong answer. And I'm not just saying technically the wrong answer. It's also morally the wrong answer. Do you want to go home and explain to your kids what you have been doing at work? Using Java 8 in 2019? Of course you don't. That's not a discussion anybody wants to have with their loved ones. No, instead, we're going to use the correct latest version of Java because it works great. Now, we're going to bring in support for building reactive web applications. Okay, I'm going to bring in Lombok. I'm going to bring in R2DBC, which is a nice API for building reactive SQL data access, supporting reactive SQL data store access. We're going to use Postgres. I like Postgres here. We're going to bring that in. And I'm going to use RSocket, okay? So we've got a number of different APIs, and we're going to hit Generate, and that'll give us a new project, which I'm going to open up, as I always do, in my IDE. Let's go ahead and get rid of all that, hit Generate. All right. Now, here's my zip file. And what we're going to do is we're going to open this application up, and we're going to build an application that very quickly talks to a database and so on. So here we go. A brand new reactive web application. There, okay. Here we are. It's a new application. Is that font a little small? Let me make that a little larger, friends. I never know. Okay, good. Now, we have an application. We're going to write data to the database. I am going to be using Postgres. Now, I have, on my database here, my class path, I have an experimental new project called called R2DBC. I have support for an experimental new project called R2DBC. What we're going to do is we're going to support reactive data access here. And you can see that we've already retooled the Spring Data portfolio projects to support, wherever possible and feasible, these reactive data access options. Up until recently, we've only had support for reactive NoSQL data access, things like MongoDB, Couchbase, Cassandra, and Redis. But now, in the last year or so, we've been working on this thing called R2DBC. I suppose it's now almost 2 years. We've been working on this thing called R2DBC, which is Reactive SQL Data Store Access. So I've gone to the Spring Initializer, I've selected it, and you can see I've already got the R2DBC Postgres implementation, and I've got the support for Spring Boot and R2DBC. So I'm going to write this, I'm going to map this application to a table in my Postgres database, okay? It's going to be a private integer ID, that's my ID, my monotonically incrementing primary key. It's going to be a Java entity, of course. I'm going to have some getters and some setters and toString and all that kind of stuff. And I'll create a field here called name. And there we are. That's the entire entity. Now, what I want to do is read. I want to actually write some data to the database. In order to support that data access logic, I'm going to create a repository, okay? A reservation repository. It's going to extend the reactive CRUD repository, supporting entities of types reservation whose primary keys of type integer. Now this interface is a very simple Spartan kind of interface. If you extend this interface, if you provide an interface that extends this interface, you will be given an object that provides methods that satisfy all these different API calls. So you can see there's the usual suspects. You've got save, save all, find by ID, exists, count, delete, etc. All these things should be fairly straightforward if you've ever seen Spring Data before. What is, I think, a little novel are the types that are specified here as parameter and return values. The first and most important of which I think is a publisher. A publisher comes from the reactive stream specification. It publishes data asynchronously to a subscriber that then listens to that data. And each time a subscriber subscribes to a publisher, the onSubscribe method is called once, and you are given a subscription reference. We're going to come back to this in a second. When new items have been published by the publisher, asynchronously and out of band, they are delivered one by one to the onNext method in your subscriber. If there are any errors, when there are any errors, the onError method gets called. And this is very important, by the way. We signal and process errors using a callback. We don't expect you to use the try-catch control flow mechanism. And the reason is because, well, of course, with reactive programming, code will jump the flow of execution from one thread to another. Stack traces are thread bound, right? We have now the possibility of having errors that propagate across multiple threads. So here is how you get those errors, how that gets propagated. When you are done processing data, the onComplete method will be called for you. Okay? So these are this is the very simple dynamic. You've got publisher and you've got subscriber. I mentioned that when you subscribe, you are given a subscription. And this is arguably the most important part. It's in this subscription that you, the client, can ask the publisher to give you more data or, as importantly, to not give you any more data, to slow down in effect. This is client-managed flow control, and it's critical in building stable, robust, distributed systems. Is you need the ability to specify at what rate you, the consumer, will consume data or will consume messages. This is client-managed flow control. It's a very simple thing. If you've ever written any kind of network protocol at all, you've had to think about this, right? Flow control between one node and another. It's something that we've had to think about, in truth, ever since there was one computer on the same network as another one at all, ever in the history of computers, right? Flow control is a very old idea, but it's been given a very new marketing name called back pressure. Okay, back pressure is what you might have otherwise heard of. Back pressure just means flow control. It means the ability to slow down the rate of publication on the publisher's side. Okay. Now, I said that this reactive stream specification is a sort of de facto extraction of common ground interfaces. It was created by a number of different vendors that know about this. The Pivotal Reactor team contributed to this effort, of course. Lightbend contributed to it. The Eclipse Foundation contributed to it. Netflix, of course, contributed to it. So a lot of different organizations define these interfaces, and we publish them. They're so obviously useful, my friends, that they have since been incorporated into now a creakingly old, ancient version of Java, Java 9, that came out 2 years ago, okay? Almost more than 2 years ago. So if you look at Java util concurrent flow.processor.subscription.subscriber and .publisher, right? These types have been copied line for line inside of the JDK. So now when you talk about reactive programming, and I said that these types have to be ubiquitous, I mean truly ubiquitous. They're now available in every JDK out there, right? Okay, so we have these basic types. They're, by the way, interchangeable. A lot of the reactive projects that you use, such as Pivotal's Reactor, which underpins Spring, will support both Java util concurrent flow types and the org reactive streams types, okay? Because they're, save for the package, they are identical in signature. Now, we have this repository. It provides, it supports and it accepts publishers, but publishers, I think you can agree, are fairly Spartan things. They don't do a lot. They're just things that publish data to subscribers, but they don't provide facilities for the sort of smooth management or operation on data, right? How do I filter or map or flat map data streams? And so here is where Pivotal's Reactor can provide two specializations, the first of which is a mono. A mono is a publisher that produces 1 or 0 values, okay? It's a thing that produces at most 1 value. It's like a completable future with back pressure. And it provides all these extra operators, very nice operators, that you can use to support mapping and flat mapping and merging and all that kind of stuff. We also have a Flux. Now, a Flux is also a publisher, but it produces potentially unbounded, unlimited amounts of data. Okay, they're both publishers. You can pass them around, and they work interoperably with things like RxJava from Netflix or Akka Streams from Lightbend, etc. All support these types. But if you want to use Flux and Mono, you get some extra semantics and some extra utilities there. Okay. Now we've got that basic repository. Let's write some data to the database, a sample data initializer. Okay. And here I'm just going to create a thing that listens for an application-ready event. So when the event gets published, we're going to listen for that event, and we're going to process it in this bean that we're going to create in Spring that's going to be called when the application starts up. We're also going to inject our repository. Okay, I'm going to inject that. I want a constructor. I could create the constructor myself, but I find that using Lumbuk's required arg constructor is nice. It'll generate a constructor that takes a parameter of the type of all final fields in the class. That means that Spring will automatically provide it for me. And what I'm going to do is I'm going to create some data. I'm just going to write it to the database. Let's list some people on the Spring team. So, of course, we've got Phil. Okay, we've got Phil. Good stuff. We've got Madura, of course. We've got me. That's me. I'm Josh. Nice to meet you. We've got Olga. Good. We've got, that's 4, I guess, and we need 4 more. So we've got Cornelia. Okay. We've got Stefan. Okay, we've got Violetta, and we've got Dave. Okay, so there's a number of different names there, just some names on the Spring team. I'm going to assign that to a publisher, a reactive stream of names like this. Now, of course, it's Java 12, so we can just do that. That's nice. And then for each one of those names, I'm going to map over them, each one, and I'm going to write it to the database, right, like so. Okay, there's this. And that gives me a stream of reservations. But what I want is to write this to the database. I've created the new objects. Now I'm going to say reservations dot, well, what am I going to say? I could say map like this, right, and pass that in. But look what happens when I call .save. I get a mono of reservation. So if you look at the contract, the result, I get publisher of mono of reservation. That's not what I want at all. What I want is just flux of reservations. So in order to unpack that intermediate publisher, that intermediate mono, I'm going to use flat map. Now, if I run this code as written, even though there's a lot of code here, nothing is going to happen. You see, these publishers are like pipelines. You've created the pipelines, you've defined how the pipes connect together, but there's no data in the pipe. You haven't turned on the water, so to speak. We call this a cold stream. In order for it to become a hot stream, you subscribe. Okay? So I could say save.subscribe, but I want to clean up my database here a little bit, because think about what's going to happen. As I run this code, it's going to, over successive runs, write the same data over and over to the database. And I don't want the same data over and over. I just want to have just the 8 records. So before I subscribe, what I want to do is I want to say delete everything first, and then pass in names to run that, and then I want to find all the data, and then finally, I want to log the results out, okay? And I can call one of the overloaded versions of subscribe. I'm going to inject a logger using Lombok. That's a nice tool there as well. Okay, so there's my application. One other thing I like to do, just because, why not? I use this a lot, is the lazy initialization. It matches the way I feel as a human being, so let's just use that. Okay, here we go. Let it compile for the first time. Uh-oh. It's saying that I need to specify a URL for my R2DBC database connection, and I think that's a good point. So cat desktop misc deps R2DBC. All right. Application.properties. There we go. So I'm going to say spring.r2dbc.url equals this username and password on this host with this port and this database schema, okay? With that done, I'll restart. Here we go. Okay, there's our application. Let me restart that again, shake out all the dust. Okay, there's our application now. And you can see that it worked. There we are, huh? There's our 8 names. It's been written to the database successfully. It worked. Of course it worked. It was a demo. What were you expecting? No, that was always going to work. As always, really why I'm here, why I flew to San Francisco to be here with you today, is to talk about what a matter of what I think is grave importance, right, of grave importance. Do you see this ASCII artwork here? This artwork took a long time to get right. But we on the Spring team have many people who are doctors, PhDs, people who worked on this ASCII art so that you didn't have to. And so for this reason, I'm going to take a brief moment, just a brief moment, to talk about what I consider to be a glaring and serious deficiency in the IntelliJ JetBrains product. For while I'm a fan, I consider this to be particularly short-sighted. Do you see this checkbox right here? Do you see this one right here? This one. That one there. That one. That one right there. If you see that checkbox, then you understand that it actually disables the ASCII artwork. It suppresses the output of the ASCII artwork. What the hell? Why is that there? That's a dumb feature. And so I did what all people would do in this situation. You don't have to thank me. I'm not a hero. I just went on the internet and I cried. And I was given a message of hope from my friend Jan Sabran. This is Jan Sabran. He's a developer advocate at JetBrains. This is him right here. That's him. That's him. Boop. Anyway, he sent me this message of hope, which I want to share with you here today. I want to believe him. I've known him for a long time. We are friends. He said, "Don't worry, Josh. We're going to fix it. It's going to be fixed, no problem. Just relax, man. Just chill, he says. And you know what? We've been friends a long time. Every release, he says that to me. He says, don't worry. And you know what? I want to believe him. We've been friends a long time. I really want to believe him, but I'm just starting to think that maybe, just maybe, he's not on the level. Whatever. Anyway, I have great ASCII artwork in the database, and we have got data in the database. Now, what I want to do, and by the way, we can actually go into Postgres here and confirm as much, I guess. That's a good idea. Okay, so select all from reservation. There we are. And, dereservation. There's this. Now, we're using R2DBC. This is a reactive abstraction. There is no synchronous blocking I/O underneath. This is a complete re-implementation of the driver, of the protocol to communicate with PostgreSQL. We'll have, in the R2DBC project, already preliminary support for Microsoft SQL Server, for PostgreSQL, for H2. There's a third-party one for MySQL as well, and more coming all the time. So you're in good shape when it comes to talking to SQL data stores in a reactive, non-blocking way. This doesn't use JDBC. Obviously, we can't, because that was a blocking API. Now, we have got data in the database. I want to build an HTTP API. I could use an at-rest controller. That's a very natural option, but I'm quite keen on this functional reactive style here. So what I'm going to do is I'm going to create a server response, like so. Okay, so return route and build at get, okay, /reservations. And I'm going to create a new handler function. And this handler function's job is to produce the response. So I'm going to inject the reservation repository. I'll say server response.ok.body, passing in rr.findAll. Okay? So that's just me returning all the data when asked. When somebody makes an HTTP GET call, I return the data. And of course, this can be cleaned up with static imports and so on. That's my entire HTTP endpoint. There's an @GET predicate and a handler. And I can do other things as well. I can chain them together, right? This is just a builder API after all. So you have lots of flexibility there in controlling routes. Let's go ahead and bring that up and let's see what we get. Yep. Okay, there's our data. There's our little web application. And this is, nothing fancy about that, of course, right? It's just a simple endpoint. And it's just a web application. But keep in mind, this is not like a servlet application. There is no servlet API here. This is a brand new reactive web runtime built on Netty, okay, that we provided out of the box. And so you can use servlet. You can use the servlet API if you want to, but by default you'll get this, and I think you'll find it's quite nice. Now, I just showed you how to do JSON while talking to a SQL data store, and I can hear you complain. Who cares? I could have done that yesterday, right? I don't need reactive to talk to a SQL data store and return 8 records of JSON. Fair point. Where reactive programming really comes into its own is in all the different places where you might monopolize, where you might otherwise monopolize a thread on the server side. So what things typically require you to block a thread or to monopolize a thread on the server side, thus making it expensive to handle a request? Well, typically things that need ongoing data, that need liveliness, right? So anytime you've got a long stream of data, maybe you've got a large amount of data, that's a good example of something that might monopolize a thread. Anytime you want to send status updates, you want to do live, presence or stock tickers or just any kind of ticker at all, anything where you want to do server-initiated push, these are things that would otherwise monopolize the thread. So what we're going to do is we're going to create a simple thing that's going to produce a never-ending stream of data, okay? And then we're going to communicate that to the client using WebSockets. So let's create a greetings service, okay? It's just a thing that's going to produce a stream of greeting response objects, okay? Greet, and we're going to have a DTO here, and we're going to have a greetings request, of course. So when somebody sends a request, giving a name, we'll send back a greetings response giving a message, all right? There's that. Now, these are DTOs, so we're going to have just data at allRx constructor, at noRx constructor, and voila, okay? There's this. Now, we're going to say, given a greetings request, we're going to send back a never-ending stream of responses, like so. In order to do that, I'm going to use one of the operators on Flux. So I'm going to say, give me a Flux based on a stream, and I'm going to generate a Java 8 stream, returning a new greeting response. Hello. Request.getName at instant.now, okay? And voila, Okay? Now that's a never-ending stream. That's going to produce a new value forever and ever. And the problem is that this is actually going to produce a new value as fast as the consumer can take it, right? And no faster, of course, but still, it's going to go so fast it'll just scroll right off of our console and onto the floor, and eventually my log itself will kind of get into trouble. So I'm going to stagger it a little bit by introducing a delay. And I can do that because behind the scenes, Reactor provides a scheduler. That scheduler is what moves work in these reactive pipelines that we've just built from one thread to another as needed to support our computation. We can override that pipeline. We can override the movement, the scheduler that does the movement of work from one thing to another if we want to. So I could say, for example, subscribe on and provide a scheduler like so. But you don't need to. In fact, I would say that if you're doing this, you're probably doing something wrong. You shouldn't need to do this, right? We have an event loop. Each thread is an event loop. Each thread will work just fine as long as you don't block. And if you do block, if you do something that talks to a SQL data store using JDBC or using something that does synchronous blocking HTTP, then may I recommend that you take a look at our little project called Blockhound. Blockhound is a Java agent that we created that you can just add to your class path, and it'll automatically throw an exception when you do something that blocks a thread on a thread that should be a non-blocking event loop, okay? It's called Blockhound under Reactor, and it works with other frameworks. It doesn't have to just be Reactor. It can work with RxJava and Akka and whatever, right? You can easily adapt it if it doesn't support it already. Now, we've got this simple greeting service. Now, let's create a WebSocket endpoint, okay? Greeting WebSocket config. And it's just going to be a Spring Bean that's going to provide a WebSocket handler. And this is going to be the thing that actually has the business logic. So a new WebSocket handler. In order to do this work, though, we need two other things. We need a simple URL handler mapping. This is going to be the thing that actually maps the WebSocket upgrade HTTP endpoint to the WebSocket protocol. So it's telling Spring Webflux how to map the WebSocket HTTP endpoint, the upgrade endpoint, to this business logic represented by this WebSocket handler that we're going to implement here in a second, okay? So there's this. WSH, going to order it as number 10. Okay, good stuff. And finally, we need a WebSocket handler adapter. This is also just fairly ceremonial. We'll just get rid of that. Good. Now, we're going to inject our greeting service, and we're going to use that to satisfy this request here, okay? So imagine what's going to happen. We're going to have a WebSocket client. It's going to connect to our WebSocket service. It's going to send on the WebSocket protocol a request containing, for example, a name, Josh or Jane or whatever, and then we're going to send back a series of greetings delivered in perpetuity every second for the rest of existence, okay? As long as there's heat in the universe, this code will keep running. So we're going to say session.send. And what are we going to send? Well, we're going to send the result of processing the data that comes in, which is a publisher of WebSocket messages. For each WebSocket message, we're going to extract out the payload. This is the name, after all, right? And then we're going to var, okay? Then we're going to say, for each one of those, let's map each name into a new greetings request, okay, passing that in. And then for each one of those, I want to flat map. I want to call the greetings service.greet with each new greeting request, all right? And then for each one of those, each one of the greetings that comes back, I'm going to map over it and get the text out of it. And then for each one of those, we're going to take that and convert it into a WebSocket text message by calling session.textMessage, passing in text. And we're going to send that all back. That's the entire discussion between the client and the service, okay? So we're sending that. And of course, this can be rewritten like this. There we go. Now we have a WebSocket handler. In order to demonstrate all this, of course, I need to do something that I'm not proud of, something that I wouldn't do in polite company if I felt there was a more expedient way, but I'm afraid this is the best I can do. I'm going to write JavaScript. So, directory, source main resources, static, and create a new file here called ws.html, in which I will create an HTML file, a body element, a script element, and I'm going to say window.addEventListener, and we're going to say load function var ws equals new WebSocket ws localhost 8080/WS greetings, okay? ws.addEventListener open, so when the socket first connects and it's live and we can actually use it to send data, that's the callback that we're going to expect. And then when the messages arrive, we're going to have the onMessage callback, okay? So here are our two chances to interact with that WebSocket. We're going to send a name, so we can say, who do we want to talk to? Who do we want to say hello? Actually, just to send Duke. There we go. Okay, there's Duke. So we're going to send that string. And as each result comes back, we're going to log out the result. So we're going to say, hello, e.data, okay? Or just e.data, actually, that's even better. Okay, now let's restart. Okay, so now we've got this application, localhost, ws.html, and you can see that every second in the console, in the developer tools there, it's showing a new updated message. That WebSocket service is going to produce a new value, updating every second for the rest of history, for the rest of humanity, right? The rest of our time on this planet. As long as there's heat in the universe, like I said, that's going to keep going, and that's okay, because it's not keeping that thread open. In between the raindrops, that thread is freed up, and somebody else can reuse it for other things on the service. So it's a very efficient way to scale. Reactive programming allows us to handle more requests with the same hardware. It's not about making any one transaction faster. In actual time, it might even be a few milliseconds or microseconds slower. But we can do more with the same hardware. We can handle more requests with the same machine. So we have now a service. Let's briefly build a client. We're going to go back to our reservation service. I'm going to build a edge service, okay? I'm going to call it the edge service. And same thing as before. I'm going to have a few options here. So I'm going to say use Java 12, because that's the right thing to do. And then we're going to search for a few APIs. Spring Cloud Gateway, we're going to use Lombok, we're going to use Reactive Web, we're going to use RSocket. And I think that's it. I think that's all that I want. So I'm going to hit generate, and that'll give me yet another project. And here we're going to build a new service that's going to talk to the API that we just built. And this is going to be an edge service. It's going to be a thing that sits there at the edge of our architecture, processing, fielding inbound requests for requests to the downstream service. It's going to start processing them. So let's see, cd edge service, idea pom.xml. What happened there? Window. Okay, open. Downloads. I feel like this should be easier. Yes, open as a project now. New window. Okay, so it's going to be an edge service. It's going to be the first port of call for requests that come in from the outside world. These things are going to be in all sorts of different shapes and sizes: iPhones, Androids, devices, PlayStations, Xboxes, smart TVs, etc. And all of them have their own different concerns. So it's very common to have a place where you can handle cross-cutting concerns and also client-specific concerns, rather than having to burden every single downstream microservice with these responsibilities. And we do that here at the edge service. There are two different kinds of edge services. One is a gateway, an API gateway. So I'm going to go here. My application will run on a different port, of course, because I don't want to conflict with the other one. It's going to run on port 9999. And one thing I can use is Spring Cloud Gateway. So it's a nice little reactive project that allows us to describe pipelines, basically. So as we match an incoming request, an incoming route, we forward the route, the incoming request based on the rules that we specify here in the routes builder. So we say route spec. Oh, sorry. Okay, route. Okay. Route spec, rspec dot path. So I'm going to say when something comes into port 9999 and has a path of proxy and a host of star.spring.io, then I want to forward that request to my microservice running on port 8080, right? There it is, reservations. Now, of course, I want to send it to reservations, but the path on the incoming request, as we can see here, is proxy. And so the request will be /proxy as the path. It'll get sent unadulterated to localhost 8080 /proxy, but I want to go to reservations. So what I need to do is to process this request, transform it before it gets sent here. And I do that with a filter. A filter is a thing that allows you to do all sorts of interesting things, not least of which is change the path of request. You can add rate limiters, right? You can do a rate limiter. You can do add response body, response headers, for example. So HTTP headers.access control allow origin could be provided there, for example. You can do all sorts of stuff there. But either way, you've just created a little micro proxy. Okay? Now, this is one way to create an edge service. Another is to create an API adapter. Now, an API adapter is great for anything you want to do that transforms a request, right? API gateways are great for generic, cross-cutting kinds of transformations that don't have any awareness. They're ignorant of the payload that's being conducted over the wire. But an API adapter will modify the payload. Maybe you'll take data from here and from there and then synthesize a new endpoint based on that data. Maybe you enrich the data. Maybe you subtract or filter the data. Whatever you're doing, you do that in an API adapter. And we don't actually have to create a separate project for that because it turns out that this is an absolutely critically great way to create applications or these kinds of services already, right? So we have now this route endpoint, and we're going to create a request. We're going to create an endpoint that provides just the names, okay? It's going to transform the data that comes in and provide just the names. In order to do that, we're going to make a reactive web call, a reactive client-side HTTP call to the other service, like so. So web client .builder build. Okay, there's my reactive HTTP client. I'm going to inject that here, web client, and I can just make a call. I can say client.get.uri HTTP localhost 8080/reservations. And as the data comes back, I'm going to take it and turn it into a stream of reservation objects. So I'm going to take the JSON that comes back and turn it into a reactive stream. In order to do that, though, I need the type for reservation. So I'm going to do something terrible, something that you should never, ever do, ever, not even when you're all by yourself at home and no one is looking. I am going to copy and paste code. So I'm going to go here, get my reservation entity, paste that here. We're going to go get the reservation, the greetings response and greetings request entities as well, the DTOs. Paste those here. And now I can create this new endpoint, this new reactive endpoint as I want. So var reservations. And remember, I'm not actually sending the reservations to my client here, right? That would be pointless. I'm going to send an enrichment of the data. I'm going to actually filter the data and get only the names. So here we are, reservations.map r get name. So there's that. Okay, string.class. Now this is a very simple API adapter. All I'm doing is I'm processing the data, just like you could do with any other stream. And you can build in more robustness into your API here. You can say, okay, if there's an error, then I want to, given an exception, return a default value there, etc. I can do a retry, for example, if something goes wrong. I can even do a retry and back off, right, like so. All sorts of very smart things you can do there to make your code more robust because you are making a network call there, right? One thing that's really quite nice is that, remember, here, I have just a publisher of reservation, right? This is just a stream of reservations, publisher of strings, but I'm making a network call. There's no reason that I couldn't make two network calls and actually pick the first one that responds and send that back. So imagine I have an SLA, and I want to be guaranteed that if I have a very tight SLA, that something is going to produce a response in time. This is a very natural thing to do. If you have two publishers and you call the same service on host 1 and host 2, and you want to get the first one back, it's very easy to express that. You can say host 1, and I'll leave you to the do that. Okay, host 2, and you just say, hey, I want the first one that returns. That way, I'm guaranteed that something will return in time. I can just say flux.first, right? This is called hedging, like hedging your bet, right? It's a very natural call. Here you just make a network call just like I did above there, but now you're guaranteed that the first one that you need will respond. Obviously, you're making two network calls, and so this is slightly inefficient, but it does guarantee that something is going to work fastest, right? You should not use that, by the way, on the charge the customer credit card endpoint. That's not going to be great, obviously. Okay, so we've got a number of ways to make our code more robust. This is for HTTP. We have 1 minute, so let's talk about one more thing called RSocket. Now, RSocket is a binary protocol. It's a network protocol that is natively reactive. It gets around some of the limitations in HTTP, the things that make it pretty unscalable for any kind of large sort of HTTP microservice-based environment, right? So Facebook, Netflix, Alibaba, they're all discovering that HTTP just at some point becomes a saturation point. So they created a network protocol over at Facebook. The engineers at Netflix started it, and they moved over to Facebook. And there, they created this binary protocol that is natively reactive. It supports 4 different message exchange patterns. You have a message in, message out. You have a stream in, stream out. You have a message in or a stream in and no value out. You can do either bidirectional communication. It's a stateful, multiplexed connection. So it's just a really nice protocol. And it's payload agnostic, right? So it doesn't matter what you use. And it's built into Spring Framework 5.2. So let's quickly, very, very quickly, take our existing service here, the greetings service, and make it a greetings RSocket controller, okay? So I'm going to rework that to be a controller, and I'll map it like this, greetings. And that's all you need to do to support it. Now, this protocol is already supported in Spring Framework 5.2, which is what we're using here. And over here on the client, I'm going to build a new edge service, a new API adapter that's going to just produce a greetings stream of server-sent events. That's kind of like, it's like WebSockets, but HTTP-based, okay? So I'm going to say return server response.ok.body, and the data that we're going to send is going to be based on the RSocket requester. That's the client that you can use for the RSocket protocol. So rc.route greetings.data, and the data that we're going to send in will be the name turned into a new greetings request, right? So r.pathVariable name, right? There's that. And the data that we expect back will be a series of greetings responses. And that's it. That's the entire thing. So take this. Good. var data equals this. There's the network call. Okay, we're making an RSocket reactive protocol wire protocol call. As the data comes back, we say data, and it's going to be a stream of greetings responses. Now, of course, this is going to be JSON by default. I want to tell my runtime to treat it as a service and event stream. So I'll say media type text event stream. Okay, but otherwise that should look very familiar, right? Just a very simple endpoint there. Let's see. Compiler says what? Okay, there we are. Looks like we're okay. What's unhappy right now? RC. Oh, I need to create that bean. So we need the RSocket requester. Same basic approach. RSocket requester dot builder and return builder dot connect to TCP localhost port 707077. Okay, there it is. That's the entire thing. Looks almost identical to the web client, the HTTP non-blocking web client. So I'm going to stop and restart. All right, so localhost greetings Duke. Okay. Whoops. Which endpoint? Greetings. What? Adapter. Greetings. Did I not do that right? When in doubt, recompile. I don't see. Okay, I mean, this is very strange. What is going on? I don't see the, okay, wait. GW, route locator builder, adapter, web client, WC, RC, okay, gateway. I'm going to comment that out because I don't care enough. Okay, goodbye. Take 2. Let's see if that makes a difference. I don't know why it would. Oh. That is so awkward. Okay. No, it's 999. That's the HTTP endpoint. So yeah, you're right. Now I get it. Thank you. Haste makes waste, friends. Don't do what I did. So we have the gateway code there? No, we didn't. Restore that. Let's do that. Go. Okay. $99.99. This is the edge service. Good, right? There we go. It's making an RSocket binary call, and then it's making a call to the reservation service. It's getting the stream back, and it's sending back that data as a stream using HTTP on the client, right? So we can integrate with the HTTP world, but we can speak RSocket from service to service. And we also have the gateway code, right? So I can also go to the gateway endpoint. I can say -h host duke.spring.io HTTP localhost 9999 / reservations names. Okay, and there we are. There's our names that we get back using that Spring Cloud Gateway. All right, my friends, I hope you learned something. I hope you got something new out of this. We've only just begun to cover the basics of this stuff. There's so much more interesting stuff that we could talk about. This technology is being used by small companies like Netflix, like Alibaba, and so on. I think there's going to be a lot of interesting opportunities here. I want to thank you for your time. I'm doing a talk on testing on Wednesday. I think afternoon, morning, something. It's beautiful testing. Come to that. It'll be fine. It won't be the worst mistake you make that hour. All right. Thank you so much, everybody. I appreciate it.